Hello class, and thank you for watching. In lesson 6.3, titled Logarithmic Functions, we're going to begin by defining what a log function is and focusing on how to rewrite it as an exponential equation and how that applies to evaluating log functions. Let's begin, like I said, with the definition of a log. A log function is the following. So for the values of x greater than 0 and a base b greater than 0, not equal to 1, the equation y equals log base b of x is equivalent to the concept of b raised to the power of y equals to x.
So in the first part right here in example 1 and 2, what I want to focus on is how to rewrite these log functions into exponential form. Now, again, the equivalency between these two things is that a log function is essentially an exponential. And what we're doing here is getting this base b, we're here, raising it to this power of y, the value of the log, and that power is going to equal again to the value of our log. So here we're evaluating our log at a number x. So b to the y power will end up equaling to x. And that would be the exponential form, converting this equation into this equation right there. So let's look at the examples that we have right here. So for example 1a, to write this equation in exponential form, we're going to look at the base, so 5. Raise that 5 to the second power. So 5 to the second power. And the value of 5 to the second power is going to equal to the value of the log, which is the value of x. So this equation here, let me move this over here to the side. This equation here is equivalent to the concept that the log base 5 of x equals to the value of 2. So let's look at the next example. Let's look at 1b. So here we have the common log. So let me write it like this. The common log means that the base on this one is 10. So the common log of 10, log base 10 of this 1,000 equals to the answer of 3. Well, what's going to be the equivalent exponential form? So if I get the base of 10, raise it to the third power, that's going to end up equaling to 1,000. And mathematically, again, look how that makes perfect sense. If I check again, 10 to the third power, that means multiplying 10 times 10 times 10. Yes, it does in fact equal to 1,000. So what we're practicing here is given a logarithmic equation, how does that correlate and translate to an exponential equation? And here it equals to that. Now, let's do one with natural logs. Recall that a natural log means that our log has a base e. So we need to read this notation, sorry, that's kind of thick right there, this notation of ln as log base e of the value of x. So this is going to end up equaling to that value of y. So that means as an exponential equation, our base of e raised to the power of y equals to the value of the natural log, which is the letter x. So there's your equivalent exponential equation. Now let's practice now going the opposite direction. Now let's write an exponential equation into its equivalent logarithmic form. So to do that, you'll notice again that the base of the log matches again the base to the exponential equation. And the value of the log, again, is the solution to the exponential equation here. The answer to this is going to end up equaling to the exponent to this base. So let's look at example 2a. So here, to write this equation into its equivalent logarithmic form, I'm going to write again, obviously, the word log. And the base of this log is going to be the base to the power. So here we have 12 to the second power, and the base of that power is 12. So that means that the base of the log is going to be 12. So that's a subscript. The value of the log is the solution to this exponential equation, which is the number x, or we don't know what x is. So x. And this is going to be a total of an exponent of 2. So let's say we had something a little bit more specific. So with some actual numbers here, let me move this underneath this. And let's actually write what the value of 12 to the second power is. 12 to the second power equals to 144. So you see, we have a true exponential equation with an actual solution. So what does this look like again in logarithmic form? In logarithmic form, this would be log with base 12 of this value of 144. And notice what the solution of this is. The solution to this log is the value of 2, which again is the purpose of this video, understanding this concept. That what we're doing with a log and how we're going to evaluate a log correlates to understanding how many factors of this base I need in order to get this 144. So I need 2 factors. Since the solution is 2, that means I need 2 factors of 12, which means 12 times 12. Again, 2 factors of 12 equal to that value. Okay, so keep that in mind when we work on the next example, example 3. So let's look at this example right here. B to the third power equals 8. So as a log, that would be a log of base B of the value of 8 equals to the exponent of 3. So now let's put some actual numbers here. Let's say this would have to be 2. If I get 2 to the third power and equals to 8, let's do an example with some actual numerical values. Look how this correlates. So as a log, an equivalent log equation, our log base 2 of the value of 8 equals to the exponent of 3. So this is equivalent to the one on the left, and this one is equivalent to the one on the right. And again, look, pay very close attention to this. What a log is doing, the solution or the value of the log, given again this number right there, correlates to this base here. It's in other words asking, how many factors of this 2 do I need to get that? That's why your solution is 3, because of this concept right there. So if I multiply 2 with 2, which is 4, and multiply another 4, that ends up again equaling to 8, like we wrote up there. And that's what the solution to these log functions are. So now let's look at this next one. So this one with the natural log. So we'll first write it again with the value of log. So we have log Since the base is the natural number, that will be again our base e. The value of our exponential equation is 9, so that's the value of the log that we're going to evaluate that. So we're going to evaluate the log with base e at the number 9, and that's going to end up equaling again to some y value there, okay? Now, in this situation, because our base is e, the proper way of writing again this log with a base e is not this format. The proper way is to indicate that we have the natural log, so ln. L for log and n for natural. Now you might be asking yourself, why is the acronym again backwards? Why is it that we have the natural log, but the abbreviation for this, or acronym for this, is ln instead of and not nl? Well, it has to do again with the language that this was originally written in. Like Spanish, the adjective is going to come in second, so we're talking about log natural. So the abbreviation for this, or the acronym for this, would be L and then N for it, okay? So it's not the other direction, because just like in Spanish, again, the adjective comes in second, what is originally written in, so we keep it again in that format. So L for logarithm and N for natural. We have the natural base, which again kind of gives it away if you look at this format right there. L again goes first, and E again is for N because it's the natural base. So you can think about it like that. But there you go. Okay, so now let's apply again what we learned on the previous page to evaluate these logs. Let's skip this top part right here real quick, and we'll focus on that in a bit. But let's look at example 3a. So how do I evaluate this? How do I determine what the answer, the solution to this is going to equal? So what is the value of log base 2 of the number 16 equal? So let me write this down. So what is this going to equal? Again, that's the question. What does this equal? Well, in order to determine what the value of this is, let's think about, again, the equivalent exponential form of this. So the log base 2 of the number 16 is the same thing as trying to determine 2 to some exponent to get the value of 16. So what we're trying to determine here is how many factors of 2 need to be multiplied before, again, so on, before I get the number 16. So let's see, let's try this right here. Let's try 5. So if I multiply 5 2's, well, 2 times 2 is going to be 4. This is going to be another 4. And then, well, 2. So this is going to be 16 already. And then times 2 more, that's going to be 32. So that I don't need the 5th extra one. So if I just do 4 of them, 2 times 2, like I mentioned earlier, is 4. Another 4, and 4 times 4 is 16. So that means I only need to multiply 4 factors of 2 to get a value of 16. So this means that 2 needs to be raised to the 4th power. So 2 to the 4th power is 16. So that's what your solution to this log is going to be. The solution to this log is going to be 4. Which again is what a log is doing. So when evaluating logs, this is what you're ultimately asking yourself. How many factors of this base do I need to get this solution of 16 in the parentheses? And whatever that factor is, that's the solution to this here. So let's see, pause the video and try the next example. See if you could figure out the answer to this question here. So now let's check again. Let's check what your answer is going to be. So right here, the question is asking us essentially how many factors of 10 do I need to multiply until I get 100? Well, that would just simply be 2 factors of 10. 10 times 10 is 100, so that means that 10 needs to be raised to the 2nd power, 2 factors of 10 to get 100. So our solution here is that the common log, which is again written like this without the 10 down there, will equal to a total of 2. So there is your answer. Now, the possibility of having a positive exponent is not the only, it's not the only possibility. Let me rephrase that. Having a positive exponent is not the only possibility. Like in this example right here. Here, I have a log of base 7, and I want to evaluate this log base 7 at 1 over 49. Which is essentially asking us how many factors of 7 do I need, how many 7s do I need to multiply to get this ratio of 1 over 49. Which is kind of weird to try to get that because I want the ratio of 1 over 49. Well, this has to do again with a fraction. So instead of trying to figure out how many 7s I need to get 1 over 49, the idea would be to get the reciprocal of that, how many 1 over 7s I need to get that value. So let's do it like this. Let's think about it like this. We should be aware that 2 factors of 7 is equal to 49. 7 to the second power. Okay, that equals to 49. Now, recall that positive exponents give you that value, but if I have a negative exponent like 7 to the negative second power, because of the negative exponent rule, that means that there's going to become 1 over 7 to the positive second power, which means that this value would be 1 over 7 times 1 over 7, which is 1 over 49. So if we know that having a positive exponent of 2 gives me 49, then to get the reciprocal of that, 1 over 49, I just simply need to get a negative exponent of that value. So here, the log base 7 of 1 over 49 ends up equaling to a negative 2 instead of a positive 2. Let's see now, you try the next example, so pause the video and see what would the value of this log equals. Let's check your answer and let's see we got the right value here. So to figure this out, let's first think about how many factors of 5 I would need to get the reciprocal of 1 over 25. So 5 times 5, that's equal to 25. 25 times another 5, that equals to a total of 125. So here I need to multiply 3 5s. So 5 to the third power will equal to 125. Since I want to get the reciprocal of that, that would mean that 5 would have to be raised to the negative third power simply. And that would be the reciprocal of 1 over 25. Of 125, I'm sorry, that would be the reciprocal of 125, which is 1 over 125. So the solution to this one will be negative 3. Okay, now let's talk about this rational exponent. If we have a root of a to some index n, this represents a real number where our index n is a number greater than 2 as an integer, then the following statement is going to be true. So if I take the nth root of some value of a, that's the equivalency of getting a and raising it to the 1 over nth power. So for example, let's say I take, let's do the third root. Let me find my roots here. It should be all the way bottom. Here it is. Let's say I find the third root of 125, okay? So the third root of 125 is equal to 5. That's the exact same thing as getting the base of 125, that value of 125, and raising that to the 1 over third power. You see how I get the same value? So we're going to use this idea again to evaluate a couple logs that have to do with square roots or third roots. So for example, look at example E. So here we want to evaluate what the log with base 25, log base 25 of 5 equals. So in exponential form, that means that 25 needs to be raised to a power in order it to equal to 5. Now the hint here is understanding again what we're trying to do. We're trying to go from this right here to that. Well, I know that 5 to the second power is equal to 25. So in order to go in the opposite direction and to figure out what power we need to get 25 to get 5, it will be the reciprocal of this value there. In other words, that if I take the square root of 25, that's going to give me the value of 5. And since what I just mentioned earlier, taking the square root is the same thing as raising it to a rational exponent, here our index is 2. So the square root of 25 is the same thing as getting 25 and raising it to the 1/2 power. So our answer right here would have to be the fraction of 1/2. So similarly here in example F, we have again come across the same situation. I have the base of 36. It needs to be raised to an exponent in order to equal again to this value of 6. Well, again, the hint here is if I go from the smaller value of 2 and I raise that, again, I should know that that to the second power equals to 36. Using that, then that would mean that in order to go in this direction, 36 would simply have to be raised to the reciprocal value of this. So the reciprocal of 2 is 1/2 in order to get to the value of 6. So as you can clearly see, that means that I've basically taken the square root of 36 to get 6, which again in exponential form is the exponent of 1/2. So in this example here, log base of 36 of 6 equals 1/2 because 36 needs to be raised to the 1/2 power in order to equal to that value there. And similarly, again, the same thing with the last two. These are actually written again in the with using rational expression. So here, the base of 2, the base of 2 needs to be raised to some power so it equals to the 5th root of 2. Well, since on the right side, the 5th root is the same thing as 2 to the 1/5, then that means that this exponent has to be the same thing. It has to also be 1/5 in order for the left and right side to equal to each other. This concept right here is called the one-to-one property of exponents, that if I have a base and I raise it to a power, let's say x, and I have the exact same base raised to another power, let's say y, then that means that the two powers, the two exponents, x and y, have to be equal to each other. Because it's the only way, again, we end up with the same value. So here, the solution to this will end up equaling to 1/5. And the same thing right here. Here, the concept between this right here is that if I get the log base 3 of 3 to the 1/7 power, as you see right there, this is simply going to end up equaling to 1/7. Which brings us again to, in the next video, we'll talk about again why this equals to this value in more detail. And it's actually, there's a shortcut to this concept whenever these bases are the same, okay? Whenever those bases are the same. But that's going to end up equaling to 1/7 again, because this base of 3 right here needs to be raised to some exponent so it equals to the 7th root of 3, which has an exponent. The 7th root of 3 is 1/7. So in order for these two numbers to be the same, I need these two values to equal to each other. Okay, so that concludes the first part to our lesson on logs on 6.3. I appreciate you watching. I hope this video was helpful. And like always, I wish you a great day and goodbye.